In Chapter 5, we will be looking at the field of chemistry that is called thermochemistry. So to get started, I'm going to give you a few terms, a few important terms that you will be using in this chapter. First of all, energy. Energy is the ability to do work or transfer heat. Now, I will say that this is a definition of energy that is very incomplete. There is a lot more to energy than this, but for purposes of this chapter, this is not a bad definition to go with. So we're going to say it's the ability to do work or transfer heat. Thermodynamics is the study of energy and its transformations. And so if we look at all the different components of energy and how energy is transformed when we are doing when we're doing any kind of process, that is thermodynamics. There is a part of thermodynamics that is called thermochemistry. It is a subset of thermodynamics, and it is the study of chemical reactions and the energy changes that involve heat. So it's just the part of thermodynamics that involves heat and work. We're going to look at the other components of thermodynamics, the other parts of it, in Chapter 19. And if you go on to become a chemistry major, you will take a whole semester on thermodynamics and kinetics and look at that particular part of chemistry. But for now, we're just going to stick with these. So first of all, we want to look at the nature of energy. And so, as we mentioned, energy is the capacity of a system to do work or transfer heat. Again, that's just a definition that we can go with. Work is the energy used to cause an object to move. Whenever a force is applied to an object and that object moves some distance, work has been done to that object or done on that object. Heat is the energy used to cause the temperature of an object to rise. And so I want to look at a piece of paper where I've got something written down. So hold on. So here I've got a system, and this system happens to be at 25 degrees Celsius. The surroundings around that system are at 24 degrees Celsius. So what we're going to find is that because there is a difference in temperature, heat will flow between one and the other. So I want you to think about what direction the heat will flow. This shouldn't be too terribly difficult. So give that a second. All right, so what direction will the heat flow? Well, it will flow from the system to the surroundings, and that's because the temperature of the system is higher than the temperature of the surroundings. And so we'll find one of the most important concepts in all of science is that heat flows from hot to cold. And if you understand that about thermodynamics, you already understand a really important concept, so that heat will flow from hot to cold. All right, so I bring that up because there are a lot of people who get very far in science. Well, no, you won't get very far in science if you don't understand that basic concept. All right. So we're going to look at the concept of kinetic energy. Kinetic energy is the energy that an object has because it is moving. So the energy associated with an object by virtue of its motion. So here we've got a bicyclist. The bicyclist is, in the first picture, is standing at the top of the hill. You can see she is at rest, so she has no kinetic energy because she is not moving. And if she were to push off and start to roll down the hill, we would find that her potential energy, which we're going to talk about in a minute, would start to decrease and her kinetic energy would increase. And as she goes faster, she would have more kinetic energy. Well, we can calculate exactly how much kinetic energy an object has, or in this case, a bicyclist, because of motion. And that energy comes out to, the kinetic energy is 1/2 the mass times the velocity squared. So m is the mass and v is the velocity of the object. And we have to not forget to square it. So calculating the kinetic energy of an object is relatively easy as long as we're just looking at the whole object. Now, it turns out calculating the kinetic energy of a person on a bicycle gets a little bit complicated because of rotational, rotational motion of the wheels and stuff. But if we were just to look at the object as a whole, we could calculate the kinetic energy. Now, before we do a problem calculating kinetic energy, I want to look at the units that are used for energy. Our official international system, or SI units of energy, is the joule. The joule is equal to 1 kilogram meter squared per second squared. And that is mostly just for dimensional analysis purposes. A joule is our official unit of energy, and we're going to calculate how many joules an object has here in just a moment. There is another, it's an older term, and it does come from chemistry. It's still in widespread use, and in fact, you guys hear about it all the time, and it is called the calorie. And the calorie, it is a dated term, but in 1948, officially, there was a group of scientists who got together and they redefined what a calorie was to an exact number. Now, I'll talk about why they had to redefine it to an exact number, but that exact number comes out to 4.184 joules, and that is an exact value. That means for dimensional analysis, or for significant figure purposes, it has an infinite number of significant figures, even though it looks like it just has 4. I mention that because sometimes you'll still see calories, and if you just multiply by 4.184, you will get how many joules that is. For kinetic energy, we want to calculate the kinetic energy of an object. So here we've got on July 9th, 2004, Randy Johnson, who is now retired, he pitched a ball in a regulation game at 102 miles per hour. And we want to calculate how much kinetic energy the baseball would have. Now, the standard baseball comes out to about 5 ounces, usually within a couple of grams of this 143 grams. So most baseballs are pretty close to that 143 grams. So we want to determine how much kinetic energy would that baseball have to have had. All right, well, the energy, RJ, Randy Johnson, is equal to 1/2 the mass times the velocity squared. Here is our mass. We do need to convert that mass into kilograms. And here is our velocity at 102 miles per hour. And then we want to convert the miles into meters. And again, this is given on the back of your periodic table. And 1 hour is 3,600 seconds, 60 seconds times 60 minutes. And then we have to square that quantity. And when we do that, the number that we're going to come up with is 149 kilograms meter squared per second squared, which that means joules. So 149 joules. So that's the amount of energy of a fastball. Now, I do like to use this Randy Johnson fastball as it's sort of my favorite unit of energy. It's kind of an arbitrary unit of energy, and it's really impressive that he was 40 years old when he did this. Somebody could pitch a ball that fast, but he was kind of an amazing pitcher. So we're going to switch back over to our document camera here. And we'll look at number 12, so 5.12. Clear all that. So we'll look at number 12 here. And it says, what is the kinetic energy in joules of a 2,750-pound Delorean traveling at 88 miles per hour? If you're not sure what a Delorean is, pause the video, go to Google, search Delorean, and you'll know what I'm talking about. All right. So in order to do this calculation, we'll do the energy is equal to 1/2 the mass times the velocity squared. All right, well, 1/2. And then our mass is 2750 pounds. And I'm putting 2750 pounds, even though pounds is a unit of force, we can convert between pounds and kilograms, the equivalent, by looking here. 1 kilogram is 2.2046. That's not an exact quantity. If we need an exact quantity, we have that number. But 2.2046 is good enough. That will give us plenty of significant figures. So we'll put 2.2046 pounds is equal to 1 kilogram. All right, so that's our mass. Our velocity is 88 miles per hour. And we need to convert that into meters per second. And so here we do have an exact conversion between miles and meters, 1,609.344. So 1609.344 meters is equal to 1 mile. And then 1 hour is 3,600 seconds. All right. And we need to make sure that we square that velocity. If we forget to square the velocity, we're going to get the wrong answer. All right, so now let's punch some numbers in. So we'll do, so 1/2, I'll just do 0.5 times 2750 divided by 2.2046. I'm going to go ahead and hit enter. That gives us that quantity. And then I'm going to multiply that by, I'm going to put this in parentheses here, 88 times 1609.344 divided by 3,600, and then close parentheses, and then we'll square that quantity. And that should give us the number that we want. And that is the number that we want there. We have 3 sig figs, so I'll write that down as 9. Oh, we don't have 3 sig figs. We have 2 sig figs. So instead of 9.65, we're going to call that 9.7 times, so 9.7 times 10 to the 1, 2, 3, 4, 5, 10 to the 5th joules. All right, so that is the energy of this car traveling at 88 miles per hour, which is quite a bit of energy. Now, as a curiosity, if we take that number and divide by 149, so I'm going to divide that by 149, that will give us the conversion to the number of Randy Johnson fastballs. So that is approximately 6.5 thousand, so 6,500 Randy Johnson fastballs. Now that, again, that is just sort of a side unit that I like to point out, but that's a lot of energy. That's a lot of energy. So obviously a vehicle going at 88 miles per hour is going to have quite a bit of energy. Now, by what factor will the kinetic energy change if the speed of the Delorean is decreased to 44 miles per hour? Well, if we look at this, since our velocity is squared, if we cut the velocity in half, then our energy is going to be cut to 1/4, because 1/2 squared is equal to 1/4. So the energy will decrease by a factor of 4. All right, so it'll decrease by a factor of 4. Of course, you could go in and actually punch that number in, and you'll see you'll get 1/4 of this 9.7 times 10 to the 5th. All right, so finally, this is a thought question here. Where does the kinetic energy of the Delorean go when the driver brakes to a stop? there's something that we haven't talked about yet, but it is actually the first law of thermodynamics. It's the conservation of energy. And it says that energy is not created or destroyed. It's only converted from one type to another. So where does that energy go? Well, since this is an old car, essentially all of that energy is going to be converted into heat. So, and it'll be done via friction. So, all right, so all of that energy will be converted into heat via friction. Now, most of it is going to be the friction between the tire and the road, or the friction between the brake calipers and the rotors, or there is some friction between the air and the car, but all of that will be summed up as friction, and it will convert all of that energy into heat, which will be quite a bit of energy. If you're ever curious, you ever see a car that's going really fast, it brakes to a stop. If you can see the rotor, if you reach in and or get like an IR thermometer thing and measure the temperature of the rotor, you'll see that the rotors can get pretty darn hot, and that is because of all of that friction. Okay. So we now want to go back to our presentation and look at potential energy. So potential energy here, again, we're going to use the bicyclist as an example. Here, the bicyclist has a relatively high potential energy to start with, and it decreases as time goes on, and her kinetic energy is increasing. Well, potential energy is the energy that an object has by its position in a field of force. Of course, her position is she's at the top of the hill, and the thing that gives her energy is the acceleration of gravity and her mass. So we'll find that the potential energy is equal to the mass times the acceleration of gravity times the height above the bottom of the hill. So m is the mass, g is the acceleration of gravity. On Earth, the acceleration of gravity averages out to about 9.80 meters per second squared. It does vary from one place on Earth to another place on Earth, depending on density of the ground beneath and where you are relative to the center axis of the Earth, and where you are relative to the equator, and a couple of factors. But overall, it comes out to about 9.8 meters per second squared. And then the height is just going to be the height in meters. We don't know what her height is, but I do have an example calculation here. So here, again, we're going to use a baseball because I love baseball. Baseball is held 106 meters above the ground. What is its potential energy due to gravity? All right, well, here we're going to use potential energy is the mass times the acceleration of gravity times the height. Again, the baseball was 143 grams. We need to put that into kilograms. We'll do the acceleration of gravity, again, at 9.80 and 106 meters. And the number that we come up with is 149 grams, which is no coincidence. That is the same amount of energy as the Randy Johnson fastball. I picked the number on purpose so that it would give us the same amount. So if you wanted to exert as much energy on a baseball, but don't have the abilities that Randy Johnson had when he was a pitching great, then you could instead go up 106 meters above the ground, which would be about the 35th floor of a building, and you could drop the ball. And the potential energy would eventually be converted into kinetic energy. It kind of just shows you just how amazingly strong Randy Johnson was. All right, so This next section, we're going to look at the first law of thermodynamics and some of the things surrounding that first law. So the first law of thermodynamics says this. It's the law of conservation of energy. Energy may not be created or destroyed, only converted from one type of energy to another type of energy. So I'm going to write that down on, if you look at number 23. All right, so number 23 says state the first law of thermodynamics. So I'm going to write that down right here. All right, through the miracle of pausing the video, I was able to write that down so that you did not have to watch me write it down. So energy may not be created or destroyed, only converted from one type of energy to another. So what that means is any energy that is lost by our system must be gained by the surroundings. This will be a big deal a little bit later. We'll talk about that. So the total amount of energy in the universe is constant. As far as we know, this is true. So we want to look at a few thermodynamic terms. One is a thermodynamic system. This is the substance or mixture of substances under study. It's the chemical system, or just sometimes called the system that we're studying. It doesn't include things that are next to it. It doesn't include the flask. It usually just includes the chemicals that we are studying. The surroundings is going to include everything that's around that system. Technically, the surroundings include everything else in the universe, but we try not to look at the entire universe while we're calculating the surroundings. We try to isolate the surroundings from the rest of the universe so that it's easy to measure changes in the surroundings. And then heat. Heat is energy that flows into or out of the system because of a difference in temperature. We saw this a little bit ago when we were looking at this, right? Here we had a system that was at 25 degrees Celsius, and we had the surroundings at 24 degrees Celsius, and so heat was going to flow from our system into our surroundings because the system was warmer. Well, if you think about it, if we go back here and look at this, well, when would it stop? And the point it would stop is when the temperature of the system and the surroundings are the same. And that's presumably going to be somewhere between 25 and 24 in this particular case. And we call that temperature, we call that status when it has stopped changing, we call that thermal equilibrium. That's the temperature at which the system and the surroundings are at the same temperature. All right. So here we've got a picture. We've got a picture of a system with some surrounding. Here the system includes some hydrogen molecules and some oxygen molecules. They are inside of a piston and a cylinder, but only the molecules count as part of the system. The surroundings are going to include the other things, the cylinder, the piston, and anything that's in the immediate vicinity of it that potentially could exchange heat or work with that system. And so that's how we differentiate our system and our surroundings. All right. We now want to look at heat, and heat is our other kinetic energy. So how much heat is added to a 143 gram, I picked 143 grams because that's the same mass as our baseball. 143 gram sample of water when the temperature is increased from 20 degrees Celsius to 100 degrees Celsius. Well, to do this, we're going to need an equation, and the equation is this, where Q is the heat, M is the mass of the water, S is the specific heat of the water, and for water that it averages out to 4.184 joules per gram degree Celsius. And then delta T is the change in temperature. And here it went from 20 to 100 degrees Celsius. So that delta T in this case is going to be 80. All right. So if we just put those numbers into this formula, we can calculate what Q is. And so Q, our mass is 143 grams. There is our specific heat, 4.184 grams per joules per gram degree Celsius. And then 100 minus 20, of course, that's 80. And that gives us 4.79 times 10 to the 4. And just in case you're wondering, that's roughly equivalent to 321 Randy Johnson fastballs. And who wouldn't be curious about that? So, okay. So there we go. That is how much energy there is. So I want you to think about this question, and after I show you the question, I want you to pause the video and think about it for a few minutes, and then I'll give you the answer. What's the difference between the ball's energy and the water's energy? Okay, so I want you to think about that for a second. So now that you've thought about it for a minute, let's look at a way of thinking about this. And so I'm going to switch over back to this, and we're going to just do a little drawing here. Okay, so on this drawing, sorry about the microphone noise. On this drawing, we want to draw our baseball. So here is our baseball. So our baseball is, here's our baseball. Our baseball is round. I'm going to go ahead and warn you, I am not an artist, but here we go. I will just put the threads on the baseball. All right, the stitches on the baseball. Okay, that's not too bad. When it comes to art, I'm not bad as a chemist, okay? And we know that the ball is moving very quickly, so here I'm going to put motion lines to indicate that it is moving very, very quickly. Over here, I'm going to draw our beaker. So here is our beaker. All right, so there is our beaker, and that beaker has some water in it. All right, so there is some water. I made the water blue. And we know that the water is hot because we've heated it up, and so I'll put some heat lines. There we go. Yeah, that's not bad. Okay. So we want to think about this. What's the difference between this energy and this energy? Well, if we look at this energy is going to be what we call the macroscopic energy. All right, and we sometimes will refer to that macroscopic energy as the external energy. When we're talking about the beaker that had the water in it, and we're talking about the heat, this is microscopic energy. And what we mean by that is the energy that the individual molecules increased. When we were talking about the baseball, it wasn't the little baseball molecules that we were interested in, it was the entire object. Whereas with this is the microscopic energy. All right, and we'll sometimes refer to that as the internal energy. Now, it is certainly possible to convert between macroscopic and microscopic energy. For example, with the car that we were discussing earlier, when it brakes to a stop, the macroscopic energy, the whole energy of the car, gets converted into microscopic energy, heat energy. However, we're going to find for purposes of chemistry, we're mostly going to be looking at the microscopic or the internal energy. And it's the energy that the individual particles have, either their potential energies or their kinetic energies. And so that is mostly what we're interested in for chemistry. Again, it's not that we don't care about this energy, it's that microscopic energy is the energy that we will discuss mostly in chemistry. Okay. So let's look at that internal energy. And we're going to call the internal energy E. In some textbooks, it'll refer to the internal energy as the uppercase letter U. but here it refers to it as E. And the internal energy is the sum of all the microscopic kinetic and potential energies of the particles making up a system. We will find that we can determine what the change in energy of the system is simply by figuring out what the internal energy is at the beginning and what the internal energy is at the end, and taking the difference between them. And we have a special word for this. We call it a state function, and we'll talk about that here in just a few minutes. We'll also find that the internal energy of our system is going to be equal to the negative of the internal energy in our surroundings. So any internal energy that's lost by our system would have to be gained by the surroundings, and vice versa. All right, so if we've got a chemical system, and here we've got the chemical system where H2O liquid gets converted into hydrogen and oxygen gas. Well, in order to make that happen, we have to add energy to our system, because the internal energy of the water is lower than the internal energy of the hydrogen and oxygen. So it would be going up in energy. The final internal energy would be greater than the initial, and so the change in internal energy would be positive. In this case, the system absorbed energy from the surroundings. If we have the reverse case, where hydrogen and oxygen come together to make water, that is going to release energy. The energy of our system, the final energy of our system, will be less than the final energy of our surrounding. So when we do final minus initial, we're going to get a negative value. And in this case, we say that the system released energy into the surroundings. Typically, that energy is released in the form of heat, but sometimes it can be released in the form of work. We'll distinguish between those here in just a minute. All right, so energy can be exchanged between our system and our surroundings in two ways: by heat and by work. And so our equation that we use for this is that delta E is equal to Q plus W, where Q is the heat and W is the work. All right, we want to look at number 23 on the in-class assignment. We had already done part A of number 23. So let me switch over here. So what is meant by the internal energy of the system? So I'm going to set that down for a second. We're going to go back. Here we go. The internal energy is the sum of all the microscopic kinetic and potential energies of the particles making up the system. And I have just written that. So the sum of all the microscopic kinetic and potential energies of the particles making up a system. And then finally, by what means can internal energy of a system increase? Well, internal energy of the system can increase in two ways, and that is by heat and by work. And so we'll go ahead and write that. So heat and work. All right, so before we're ready to answer number 25 and do a little bit of calculations with this, we're going to go back and we need to look at Q and W in terms of what does it mean when they're positive and negative, and that's what I've got here on the next page. So we know that delta E is equal to Q plus W, and so Q is the heat. And when Q is positive, that means heat flows from our surroundings into our system. The word that we use for that, since heat is absorbed, the word that we use is endothermic. Heat flows in. So endothermic, heat flows in. When Q is negative, heat flows from our system into our surroundings. And here we say heat is evolved, and we call that exothermic. And so you need to memorize what these signs mean. So heat flows in, endothermic, Q is positive. Heat flows out, exothermic, Q is negative. For work, if work is positive, Work is done on the system by the surroundings, and usually we can observe that our system will contract. So either the system contracts by itself, or we may force the system to contract by applying a force to it, so like compressing it. All right. But if our system gets smaller, it contracts, then work is done on our system by the surroundings. Conversely, if W is negative, work is done on the surroundings by our system, and that is usually indicated by our system expanding. So let's look at number 25. All right, so we'll look at number 25 here. And our formula that we're going to be using, delta E, is equal to Q plus W. Again, Q is the work, and Q is the heat, and W is the work. All right, a system absorbs 85 kilojoules of heat from its surroundings while doing 29 kilojoules of work on its surroundings. So again, delta E is equal to Q plus W. Q in this case, since it's absorbing 85, that's going to be positive 85 kilojoules. And then doing 29 kilojoules of work on the surroundings. So that's work done on the surroundings by our system. That's going to be negative 29 kilojoules. All right. And here we probably don't need a calculator for this, but 85 minus 29, and that gives us, of course, 56. So 56 kilojoules is our delta E. So it says calculate delta E and determine whether the process is endothermic or exothermic. Well, to determine whether it's endothermic or exothermic, we simply have to look at the value of Q. If Q is positive, it's endothermic. In this case, Q was positive, so this is endothermic. If Q was negative, then it would have been exothermic. All right, on this next one, the only thing that's even a challenge here is that we've got different units because it just tells us what Q and W are. So delta E is equal to 1.50 kilojoules. And then work is negative here, so we're going to put minus, and I'm going to convert that into kilojoules, 0.657 kilojoules. So 1.50 minus 0.657. And you'll see that gives us 0.843 kilojoules. Now, there's one more thing that we need to do here, and that is for significant figures. Since this is subtraction, we need to look at the place. This goes out to the hundredths place. This goes out to the thousandths place. So we're going to round this to the hundredths place. So we're going to round that to 0.84 kilojoules. And that's going to be our best answer for delta E. And then as far as is this endothermic or exothermic, since Q is positive, this is endothermic. So here we will put endothermic. All right, next, a system releases 57.5 kilojoules of heat while doing 13.5 kilojoules of work on the surroundings. All right, again, delta E is Q plus W. Since it releases 57.5, that means that Q is negative here. So negative 57.5 kilojoules. And then we do 13.5 kilojoules of work on the surroundings. Since the work is done on the surroundings, that's also going to be negative. So we'll do minus 13.5 kilojoules there. That's going to give us a total value of a delta E. I think it comes out to negative 71, but let's go ahead and put it in. So negative 57.5 minus 13.5, and that gives us negative 71.0. So negative 71.0 kilojoules. And remember your sig figs, hundredths or tenths place, so we have to round that to the tenths place. All right, and then our final bit is this endothermic or exothermic. Well, because Q is negative here, that is exothermic. So that is exothermic. All right, well, let's go back to our presentation. Work is energy used to move an object over some distance. In physics, we define work as equal to force times distance. And in chemistry, we do the same thing, but we're often talking about a gas and moving something with pressure. And so instead of doing force times distance, we're going to, since pressure is a force divided by an area, and instead of a distance, we're going to do a distance multiplied by an area, which will give us a volume. So our definition for work is going to be equal to negative P delta V. Now, the reason that the negative is there, I'll explain. Remember, when W is positive, work is done on the system by the surroundings, and when W is negative, work is done by the system on the surroundings. Well, here we've got a system. It's a piston with a cylinder, and here is our initial state, and there's our final state. Well, you'll see that our change in volume here is positive. It's increasing in volume, so delta V is positive. And the pressure is a positive number, so it is positive. So positive times the positive, but since it's expanding, that means work is done on the surroundings. So to make the math work, we put a negative in front. So that's why it is negative P delta V. All right. Let's look at a system where work is done on the surroundings, and that is this system. Oh, let me go back. So that is this system. And here we've got zinc reacting with hydrochloric acid, and it produces zinc chloride and hydrogen gas. So hydrogen gas is produced here. Well, as that hydrogen gas is produced, that's going to cause this, it's a closed system, and so it's going to cause this piston to increase. It's going to go up. So the volume of our system will increase when we do this. So drop the zinc in, it reacts with the hydrochloric acid, does a single replacement or a displacement reaction if you want to use the chapter 4 terminology, and we increase the total amount of gas in there, and so we will increase that. Conversely, we could increase the pressure, but that is not what we want to do in this case. We just want to keep the pressure constant, which is why we use this piston. All right, so that is an example where work is done by the system on the surroundings. All right, and then finally, we want to look at the concept internal energy, E, is a state function. It is a state function. We'll find that the value of a state function depends only on the present state of the system, not on the path that the system took to reach that state. And that's why this is true, that the change in internal energy is equal to final minus initial. So for state functions, if you want to figure out what the change in a state function is, you just look at where did it start, where did it end, what's the difference, and that's a state function. The opposite of a state function is a path function. And path functions, the value depends on what pathway you took. So before we go on to the next page, I want to go back to our written notes here. And I want to make a note here. So here are a few things that are state functions. So state functions. And these are going to include internal energy, which we just defined a little bit ago. We're going to have another one that's called enthalpy, H, enthalpy. We're going to define that one here in just a few minutes. We've got another one that we'll see in the second semester that's S. That one's called entropy. And then we've got another one that's G, and that's called Gibbs free energy. So this one is internal energy. This is enthalpy. And again, we're going to define that one here in a minute. This is entropy. And this is Gibbs free energy. These are all state functions. Path functions are things that are not state functions. They depend on the path. And those are going to include Q and W. Now, there may be other things that are state functions and path functions, but for energy purposes here, we're going to say that these are state functions and these are path functions. And you'll notice by convention, we make it so that the state functions have uppercase letters to represent them, and the path functions have lowercase letters. Just kind of a convenient convention that we use. All right, so here we've got two batteries that have the same internal energy. So two batteries with the same internal energy, but one of them we just hook up to a resistor and short circuit it so that we produce heat, and we can completely discharge that battery by doing this. Conversely, we could take the battery and hook it up to a little motor that turns a fan, and then that fan would apply a force to the air and move the air a distance, which means it would be doing work on the air. So it'd be doing work on the surroundings. So both of them are going, if we were to use up the battery this way and use up the battery this way, we wouldn't really be able to tell the difference between the two batteries. However, the amount of heat that is produced and the amount of work that is done would be different. And so that is, so delta E is a state function, but heat and work are not state functions. So heat and work are not state functions. So the Q and the W are different in the two cases. All right, so we're going to look at number 30. And again, if something is a state function, you just need to know where did it start and where did it end. All right, so here is number 30. All right, indicate whether each of the following is a state function or a path function. The change in potential energy when a book is transferred from a table to shelf. Well, when it's transferred from a table to a shelf, if we want to know the change in potential energy, really all we need to do is see what the potential energy was to begin with, what the potential energy was at the end, and see what the difference is. And so this is definitely going to be a state function. All right, so our change in potential energy is a state function. Because again, it doesn't matter what pathway we took with that book, whether we took it, went upstairs, came back down, and then put it on the shelf, it's still going to have the same difference in potential energy. All right, B, the heat, I could stop there, right? Heat, we know, is a path function. All right, let's go ahead and read it. The heat evolved when a cube of sugar is oxidized to CO2 and H2O. So it doesn't matter whether we took that cube of sugar and we burned it and did combustion, we would get a certain amount of heat. Or we could take that and eat the sugar, and then the amount of heat that would be produced would be a little bit different. All right, if we ate the sugar, we'd eventually convert the sugar into carbon dioxide and water, but the amount of heat that would be produced would be a little bit different based on that. So that is a path function. All right, finally, the work accomplished in burning a gallon of gasoline. Well, work, we know, is a path function. So work is a path function. If we just took a gallon of gasoline and poured it onto the ground and caught it on fire, we would get some work done. We'd push air out of the way. But if we were to take that gallon of gas and let's put it into like a really fuel efficient car, we could do quite a bit of work and move that car, apply a force to the car, move it a distance, and we would be doing work on that car. So again, the amount of work that we get done is definitely going to be a path function. All right, well, that is the end of the first video. Our next video, we're going to start talking about enthalpy.